other pre-calc classes were kind of MIA as well. So we're going to pick up today where we left off the other day. And I know it's been a while, so you might have to remind me kind of where we left off. We're on G? Okay, so page 109. We've been talking about inverse functions and one-to-one functions and trying to view or see the connection between those two terms, between those two phrases. So if we're going to pick up where G is, we're trying to first of all test to see if this equation is one-to-one. What does that mean, by the way? If it's one-to-one? Yeah.
If you were able to flip it horizontal y-axis, then if the y-axis is, there would be no repeating y's.
No repeating y's. Okay.
I just said that.
That's okay. Sometimes you got to talk about it to get there, though. Okay, so no repeating y values. So if we don't have repeating y values, when we find the inverse, which involves what? How do you find an inverse? What's the concept of an inverse? Yeah. You flip the x and the y. Okay, so if we don't have any repeating y values, when we apply the inverse, those y values would become x values. So if we don't have any repeating y's in the original, that means we don't have any repeating x's in the inverse. And that means that the inverse would be a function. So that's what we're trying to test here, the connection between the original and the inverse. Is it a function? Is it not? So taking a look at G, since it's an equation, I want you to think about what would the graph look like. Okay, picture it in your head. And then we're going to see if that graph would pass the horizontal line test. So can we describe or think about what this graph would look like? Yeah? A line. So specifically, y-intercept of -3, slope of 2/5, so angled, something like that. Would that line pass the horizontal line test? Yeah, it would only touch once, so you're good to go. So since it passes the horizontal line test, we know it is one-to-one. So we'll give that as our reason. So based off of that analysis, what do we know about the inverse? Okay, this f to the -1 power. What do you think, Eli?
That the inverse is a function.
Is a function. So if it's one-to-one, it does not have repeating y's. So that means in the inverse, it wouldn't have any repeating x's. And that fits our definition of a function. So when we actually find the inverse equation, we should be able to see how if we were to plug one thing in, we'd only get one thing out. Okay, every x has a y. So to figure out the inverse of a function, okay, again back to that concept of switching the variables, we're going to turn every y into an x and every x into a y. So this could look like x equals 2/5 y minus 3. The issue with equations, though, is you're used to seeing y equals. So this is when we're going to solve for y, just so it's a little bit more eye-appealing or comfortable for you to look at. So if we want to get this y all by itself, we can add the 3 over. Multiply the 5 over, okay. And then divide the 2. So maybe it looks something like that. Now, depending on the mathematics that you're comfortable with, some of you may have just multiplied 5 over 2 on both sides. Okay, if you did that, it might look something like this, which would be fine. Okay, you can leave it like that. But both of these are the same equation, they just look different. So depending on the algebra that you're comfortable with, your answer might look different from your partner's, but that's completely okay. All right, nonetheless, this is a function though, because if you plug one number in for x and you were to calculate the answer, you would only get one number. So one thing in, one thing out, we have that function, just like we said we should for the inverse. All right, what about h? Can we describe the shape of the graph? Go, Eli.
I can't remember what the shape is called, but it's just.
You're drawing it. Okay, so I don't really know if it has a name, but if you were to take a parabola, which is that U-shaped graph, turn it on its side, okay, to the right, and then you take the bottom half away, that's your square root graph. So parabola, side, bottom half gone. Would the shape of this graph pass the horizontal line test? Yeah, if you want to test it, it would only touch once. So 1 to 1, because passes horizontal line test. Based off of that analysis, we know the inverse is a function. So let's actually find the inverse equation, and we should be able to see at the end, if we were to plug one number in, we would only get one number out. Okay, so to find the inverse, we're going to switch the variables. And we'll solve for y. So the first thing, maybe we'll subtract the 4 over. And then we can divide the 2. Some of you might actually write this as 1/2 x minus 2, okay, depending on, again, how you write your algebra, what you're comfortable with, but they mean the same thing. Where do you want to go from there?
Both sides.
Square both sides, okay, get rid of the square root. And then subtract the 3. Alright, there's our inverse. If you were to plug one number in for x and calculate, you should only get one number for y. So we know it's a function. We doing okay? Alright, on the back page, we're going to take a look at an interesting property for inverses. Okay, some type of connection they have. So we're going to fill in this table using this g of x equation at the top, kind of our beginning equation, our beginning function. So the first column wants us to find the inverse. That's the little notation that we have, the -1 power. So we're going to go ahead and switch the variables and solve for y, just like we did in the last few examples. Remember, f of x, g of x, h of x, whatever it's talking about is the same thing as a y variable. So if we switch them, this would be x equals 3y minus 4 over 2. If we solve for y, we can multiply the 2 over. That'll get rid of the fraction, so that's a convenient step for us. And then we can add the 4 and divide by 3. All right, there's our inverse. So based off of that equation, we're going to try to fill in the other two columns. So do me a favor, take a look at this notation in the middle. What is that asking us to do? What does it look like we should try? What do you think, Emma?
To plug the inverse into the regular equation.
Into the irregular. So do you notice how the inverse is inside of g? Okay, so we're going to take this answer and we're going to plug it in for that x. And we're going to simplify it and see what happens. It's going to look a little ugly. Okay, but we're not going to judge a book by its cover. We're going to see what happens in the end. So we'll write 3. And then instead of the x, we'll substitute in that inverse equation we just found. We can continue with the minus 4, and all of that is over 2. It looks like a lot, okay, but we're going to try to simplify it, see what happens. Do you notice anything that could happen if we start to simplify? What do you see, Seth?
If
3 should cancel. This is 3 times something, and notice how in that quantity we are dividing by 3. So those are inverse operations, right? They should cancel each other out. So those are gone. So we can write what's left. Anything else going to happen? Yeah. Force cancel. 1's plus, 1's minus. Those are inverse operations, right? 2x divided by 2. We just have x, right? Because the 2's would cancel each other out. 1's being multiplied, 1's being divided. So we're just left with x. So it looked a little overwhelming, but when we actually simplify it, we get just the variable. So that's kind of convenient. Let's try the other way. So again, if you look at the notation, this time we're going to take the g of x equation, which is at the top, and we're going to plug that into the inverse equation that we found. So a very similar setup, we're just doing the reverse. So we'd have 2 times 3x minus 4 all over 2 plus 4 over 3. What's going to happen if we simplify? What do you see, Eli?
2's cancel.
2's cancel. Fours cancel. 3's cancel. We're just left with x. We got the same thing for both problems. Why do you think that is? Why does it not matter if we take the original into the inverse or the inverse into the original? Can we think about it? What do you think, Lucas? This is actually a line. So if you divided each piece individually, it would look something like that. So we're working with a line. But actually, this would happen every time, depending if it was a parabola, a line, a square root, whatever it is. Why do you think it doesn't matter? Do you notice anything special about the way the equation originally looked and the way it is for the inverse? Yeah.
Because they're like the opposite of each other. So once you go to cancel them out, it'll just come out.
Everything's going to go away. Take a look at this. In the original equation, we have a multiplication of 3, right? And in the inverse, we have a division of 3. Those are inverse operations. In the original, we have a subtraction of 4, and in the inverse, we have an addition of 4. Those are inverse operations. In the original, we have a division of 2, and in the inverse, we have a multiplication of 2. Those are inverse operations. So if all of the values are inverses, it doesn't matter what we plug in where, because they're always going to cancel each other out. So this is what's interesting about inverses. We have a way now to test to see if 2 equations are inverses of each other. We can simply take one and plug it into the other, and if all the numbers go away, meaning we just have an x value left, they completely canceled each other out. We perfectly have inverse operations in both of them. Can we see that happening with the way those are written? Okay, they're inverses of each other. They're going to undo all the values. So it doesn't matter if we take the inverse and plug it into the original, or the original and plug it into the inverse. Okay, if we get x back as our answer, all the numbers go away. That's a way for us to confirm that we have 2 equations that are inverses. So in this middle section, it said if 2 functions f and g are inverses of each other, if we were to plug one into the other and get x out, we just confirmed that they're actually inverses. So it's a convenient way for us to test this. So let's check out a few examples. So we have f and g. We want to see if these are actually inverses of each other. Now at first glance, maybe we can get a hint as to whether they are or not. For instance, notice how in f you have a multiplication of 2, but in g you have a division of 2. So those are inverses. In f you have an addition of 3, and in g you have a subtraction of 3. So those are inverses. It looks like every value or every operation has an inverse. but we actually need to test it to see if this property happens. So we got to pick what we want to do. Do you want to take the f equation and plug it into g, or do you want to take the g equation and plug it into f? It doesn't matter. You get to pick. What do you want to try, Eli?
I like to take the f equation and plug it into g.
All right, let's try it. So we're going to take 2x plus 3 and plug it in for that x. So 2x plus 3 minus 3 all over 2. If we simplify, what's going to happen? Yeah.
3's cancel out,
3's cancel,
and it's just going to be 2x over 2,
which just equals x. So notice how all the numbers canceled each other out perfectly, and we're just left with that variable. So does this confirm that these are actually inverses of each other? Yeah, they canceled each other out. We're just left with that variable. Looks good. All right, let's try the next set. At first glance, let's see if it has the ability to be inverses of each other. In f of x, we have a division of 2, and in g of x, there's a multiplication. So those are inverses. So far, that's checking out. In f of x, we have a subtraction of 1. In g of x, we have an addition of 1. So those are inverses. So we do have inverse operations there. Okay, we need to test, though, does it have this property? Do they actually cancel everything out? And we're just left with that x. So you get to pick. Do we want to put f into g or g into f? It doesn't matter. Yeah? All right. You just got to pick one of them. That's fine with me. So we'll have 2 times x over 2 minus 1, and then we need to add 1. So let's simplify it. If we distribute in the 2, we will have x minus 2, but we still have the plus 1 on the end. So it looks like if we go further, we'll have x minus 1. Are these inverses of each other? No, they didn't cancel each other out completely, because notice how we still have a number there. Remember, the property tells us that we just have an x. All the numbers go away. So based off that result, these equations are actually not inverses, even though it kind of looks like they should be. Okay, we had the division of 2, multiplication of 2, subtraction 1, addition 1. It looked like they would, but they didn't have the property necessary in order to conclude that they are actually inverses. So this is a quick, easy way for us to check. So you can't just look at the equations. They might fool you. Okay, you have to check that property of inverses. Do we see the difference between the two? We're okay with that? Okay. I know that was pretty quick for today, but that's the end of the section. So tomorrow we're going to have our free response day, and I'll let you know who your partners are for the quiz on Friday. With the remaining of the time, though, you can use as an additional homework day. Okay? So I say we have like a solid 15 minutes or so. You can get some work done.